Hello, my name's Kevin McGrath. We're presenting the real-time object detection navigation assistance system. Teammates are Vincent Eloy, myself, Max Forst, and Jack Schaefer. Our project advisor is Dr. Edith Polat. Introduction and motivation. Assistive technologies that support independent mobility for visually impaired individuals have gained increasing attention in recent years. Traditional mobility aids like white canes, guide dogs provide essential assistance but offer limited environmental awareness. Now, advances in computer vision and deep learning enable real time object detection and can improve understanding of complex environments. Our project aims to utilize AI object detection to enhance and make meaningful improvements in the lives of visually impaired individuals. Problem definition. Deploying this technology with the purpose of assisting visually impaired people by increasing their awareness presents a set of challenges. Our wearable product needs to avoid bulkiness and discomfort. The user should not be struggling with connectivity issues. They should receive audible insight without any confusion or delay in real time. Achieving a balanced system and fulfilling a certain variety of goals and parameters can be challenging. These goals lead to hardware and AI modeling selectivity needs. Work packets 1 through 10. Project management, concept generation, data set and framework setup, baseline object detection system, object state classification, environmental recognition, feedback and user interface module, system optimization and integration, testing and validation, and then finally documentation and dissemination.
The methodology that we used for designing the system was agile development. This allowed us to continuously iterate and improve certain aspects of our design as we needed. These aspects included things such as environmental recognition, object state classification, and output and UI. Once we integrated all of the parts of the system together, we ran integration tests to make sure that all the different parts worked together, and then if there were any issues, we would go back and fix them. Then we'd run regression tests to make sure that any small changes we made would not affect the system in any adverse way. We use the Yellow AI Vision platform for our project, and Yellow stands for You Only Look Once, and it's powerful because it processes the entire image through a neural network in a single pass, which makes it fast and efficient. It does this by splitting up the image into grids and then predicting bounding boxes for each object in that image. On the right hand side here you can see the graphs that Yellow generated while training one of our models, and these graphs indicate how well the model is able to recall objects and how precise its bounding boxes are. We had several difficulties along the way. Probably the most prominent was the fact that visual intelligence alone isn't powerful enough to detect things such as distances of objects or whether they're moving relative to the user or not. So to solve this issue, we implemented time of flight and inertial measurement unit sensors to help detect the distance and motion of objects respectively. Also, running the system on limited hardware was a struggle, but we have monitored the system to make it run as smooth as possible. And we also had issues with the Yellow models detecting certain objects, which we could help mitigate by training the models on more broad categories of data. And we also had physical system build issues, which pushed back the development of certain software features, but we attempted to push through and build out the system to the best of our abilities. For our hardware, we used a Raspberry Pi 4, a 5 megapixel camera, an inertial measurement unit to detect motion, 3 time of flight sensors to detect object distance, a 400 milliamp hour battery, and a set of headphones for audio feedback. And for our software, we use the YOLO V11 Nano for object detection and to give us bounding boxes and class labels. And we used our own custom object for object state classification, object distance and location calculation, and hazard prioritization. And we also utilize several Python libraries to achieve things such as audio playback and video frame processing.
The physical build of the system is housed in a 3D printed case. As you can see on the far right, we have the faceplate, which houses the TOFs, the camera, navigation buttons, and LCD readout. That way we know which mode we're currently in while we're operating the system without having to remote into the system. Then below that it houses the Raspberry Pi. Below that is also the battery powering unit. And then everything is attached on a physical rig, a harness. That way it can be worn. It roughly weighs about 8.53 ounces altogether, but with kind of extreme protrusion of about 8 centimeters outward from the chest. As you can see, here's a simple schematic of how the hardware actually connects to the Raspberry Pi. Everything is shown here except for how the battery power unit goes to the system. Pictured is the actual coverage of the camera and the time of flight sensors to verify that we are covering the full critical path plus distance to the left and right of it for any object detection necessary. The camera point of view is about 54 degrees, and each of the time of flight sensors is only about 27 degrees. Each time of flight sensor on the left and right is angled about 18 degrees to get a better spread, but there is an overlap between the three time of flight sensors, as can be seen from the color coding on the side. To ensure that the person wearing it doesn't trip over things directly below their feet, we actually angled the camera 12 degrees downward also to ensure that uh, we not only compensate for the bouncing and rising of the chest, but again, just to make sure that you can see adequately in your direct line of a path.
Performance metrics. Our system processing rate is greater than 30 frames per second. Average CPU utilization less than 50%. Memory consumption less than 75. Detection latency is less than zero point 0.1 seconds. Average accuracy greater than 90% and average confidence greater than 85.
While testing at the targeted throughput, which would have been at around 30 or greater frames per second, we had instability problems with the system, which caused it to have latency spikes and frame backlogs. And so, most likely, this is due to CPU saturation. We are unable to measure this though, because even the script that we used to measure this stuff wouldn't run and wouldn't record. The system would essentially shut down and restart. Lower frame rates. Detection actually still remained very consistent at close to 100%, but we still had the same issue with the CPU, um, which meant that again we couldn't record the exact percentage usage of everything, which is very unfortunate. But we did see the fact that it was still stable real time detection, but just not at the higher frame rates that we were hoping to get. So faster objects wouldn't be detected.
Audio feedback and user interface. Our system is going to give the user concise verbal statements. This is going to prevent information overload. Some words in these statements are variables in the algorithm, basically like your objects or numbers, for example. Um, we have preloaded statements on audio files that get queued up, such as 5 chairs on the right, person on the left, or approaching table 7 feet. Those are the things they'll hear. Queuing up versus queuing up. Funny statement. There's a difference, and for one, we're summoning relevant statements with high frequency, which is the low latency user interface that we're looking for. And then we're going to prioritize which statements will be used and in what sequence. Other controls are your on off switch and volume control.
Looking at the final design, we're going to watch a few different demonstration videos we have. This first one has a user at the supermarket with the device strapped to their chest with a person coming towards them. Watching the video, we can see that the device clearly picks up that this is a person coming towards us, along with the distance and the state of which that person is moving or stationary. The way this works is the time of flight sensors calculate the distance from the object and the user, and then the IMU gives us the acceleration of the user. We then subtract those to find out if the object is stationary or moving. There have been some time of flight sensor issues in the later builds, specifically in this area where there's light coming from the refrigerator and the glass, making it a little bit harder to detect the distance. Looking at more demonstration videos, here we have a user with the device strapped to their chest in a supermarket. On the left, we are just looking at the time of flight sensor array, which is detecting the distance of the objects close to it. When we turn the corner, we are still going to be able to detect objects, but we are unable to assign a distance to them. This is because we limited the range to just 3 meters. The reason for this is that we don't want to be notifying the user of an object when it is too far away to do anything to them. This is important when we look at the right, because here we are able to assign a classification of moving or stationary, but when we don't have the distance away from the object, we are unable to do this. The reason is that we are using the information from the IMU, including the gyroscopic and acceleration data, to tell if we are moving or not, and then comparing that with the time of flight sensor array data of the objects that it's detected, and comparing it with the distance that the object is moving on the screen. This allows us to better understand whether the object is moving or whether the user is moving and the object is stationary. In conclusion, we were able to achieve our goal of building a low-cost, open-source computer vision-enabled device to aid the visually impaired. All of the hardware used is available off the shelf, and all of the software tools are open source and available to anyone. This allowed us to maintain a balance of resource cost, financial cost, and performance while still running in real time. If we were to do future iterations of the system, we could extend the dataset to include more environments and better optimize the user experience to provide them with more environmental data. If there are any questions, we'd be happy to answer them now.